All right, let's get started. Next Monday is the second quiz. It will be from 1 to 1:10, and then again, as with the last quiz, have a 5-minute break, and then the lecture will start. I also have put up sample final questions for if you want to get a feel for the format. There's also the post on final exam. If your question is like what's going to be in there, how do I prepare for it, and all that stuff, everything that I wanted to say about those things is already in there. You should have received an email about filling in the official feedback form as an incentive for you guys to fill it in. If at least 85% of you fill it in, I'll release the first 1A question on the final, just as is. If at least 95% of you do that, I'll release 2 questions from the final. Okay. Last time when I checked, the percentage was 10. So there's a fair bit of movement to be done.
What's the typical response rate? Like, what's the usual percentage when it ends?
The previous years,
Yeah.
they haven't hit 85 yet. So they get close. So. Any questions on logistics, quiz, exams, evaluations? Yeah, Stephen. People cannot officially resign between now. But they will count, yeah. So there are 200 of you in class, and so when it says 85%, that means at least 170. Any other questions? Again, a reminder, CSET week is in roughly 2 weeks. Perhaps more importantly, the demo competition is this Thursday. So if you have not yet filled in the form, please do so. I think I sent out an email earlier today. I think there should be prizes and a bunch of fun stuff. So please do consider taking part in the competition. Stephen.
What if we're available for the demo time and not for the competition?
If you're available for the actual Kids Day but not the competition, let Devashis know and we can figure something out. Any other questions? I believe those of you in 442, Jesse has some point structure that if you do actually present on the demo day, you will get some points. So, and I believe 331 also might have something similar. So please do consider it. All right, so we were looking at, before the break, we were looking at dynamic programming. And as a reminder, there are kind of 3 rules of thumbs for using dynamic programming. The first is you want polynomially many subproblems. And so if you look back or think back to the first problem we considered for dynamic programming, which was the weighted interval scheduling problems, there were polynomially many problems. So again, remember, the weighted interval scheduling was you had n intervals and each had values or weights, and you wanted to figure out the subset of intervals that didn't conflict and had the largest total value. And so there we looked at the problem of opt of j being is the best value you can get from the first j intervals. So there you had n subproblems. And then you want to somehow have a recursive formulation of this optimal solution. And so this is the recursive formula we had for weighted interval scheduling. And you also want an ordering. So for the weighted interval scheduling, it was like if you wanted the optimal value for the first j intervals, it only depended on the optimal values for the intervals that came before it. And before the break, we were looking at the subset sum problem. And so here you're, so kind of if you were not in class on last Monday, here's kind of a hand wavy-ish motivation. So let's say you have W cycles that you bought on the cloud, and you have a bunch of jobs that you want to run. For each the ith job, you know exactly how many cycles you take. And so the question is, you just want to use up the cycles that you've already bought, and use them up as much as possible without exceeding the however many cycles you have. So the way we formulated it was you had n integers, the little w1 to wn, and you had a bound or a budget capital W, and you want to output a subset of these n jobs so that the sum of all the weights in the subset that you pick, which will also denote by ws, is at most the budget, and under that constraint you want to maximize the weight that you get. And so we looked at the following recursive formula that we derived last time. So just kind of to walk through it, we'll define opt of j comma v is the maximum value that you get from the first j numbers, w1 to wj, and the bound or budget of b. Okay. And so in particular, we are interested in opt of n comma w. So we want to look at all numbers so that the total bound is w. And so the first thing to note is if the weight of, oh sorry, this should be a b, I apologize. If the weight of the jth guy is strictly more than the budget, then the jth guy cannot be in your solution, right? So in that case, the optimal solution from 1 to j is same as the optimal solution from 1 to j minus 1, and your budget does not change. If, on the other hand, the weight or the jth number is smaller than the budget, then you have two options. So the first one is maybe picking the jth guy in the solution is not the way to go. Okay, so the jth number is not in the optimal solution from 1 to j with budget b, in which case you are looking at the optimal solution from 1 to j minus 1 with the same budget, or you do pick the jth number, in which case you get a weight of wj, and now you're left up with a smaller subproblem with the first j minus 1 numbers. But more importantly, now the budget goes down because you picked wj, so the remaining budget is b minus wj. Okay? And so we're going to use this recursive formula today to come up with the dynamic programming algorithm to solve this problem. Any questions so far? All right, so we're going to look at, say, the dynamic programming algorithm to solve this problem. All right, so I said we are looking at the subset sum problem. And I'll rewrite the recursive formula for you. So again, if wj is strictly bigger than the budget, then the optimal value get from the first j guy with budget b is same as the optimal value get from the first j minus 1 guy with the same budget b. Otherwise, you take max of two cases of whether j is in the optimal solution or not. So it's max of opt of j minus 1 comma b. And so this, what this is saying is j is not in O of j, which I'm saying is the optimal for the case of when you take the numbers w1 to wj minus 1 and you have budget of b. Or you do end up picking the jth guy, in which case you get the value, the weight of wj, and then opt of j minus 1 comma b minus wj. And again, so this j is in the optimal for, oh sorry, this is the optimal for w1 to wj. So again, the first term in the max is when the jth guy is not in the optimal solution. The second term is when j is in the optimal solution. Okay. All right, again, any questions? Because once you understand, typically for dynamic programming, once you understand the recursive formula, the rest is relatively mechanical. So we'll kind of go through them, but is everyone comfortable with this? Okay. So the way we're going to work with this is basically we're going to compute all of these values in a matrix where the columns are indexed from 0 to n and the rows are indexed from 0 to capital W. And so if I pick, say, the jth column and the bth row, then m of b comma j, ultimately you want to be opt of j comma b. So the idea is this matrix will hold all of the subproblems that I'm interested in, and ultimately I'm going to pick the one that I really want. Okay. So to do that, and just to make sure all of you guys are awake, so the first question is, which entry of M, assuming I've computed the entire matrix, are we interested in? Okay. And just recall that the input that I have are the n numbers W1 to Wn, and I have this budget of capital W.
Is it
Alex.
the top right one?
It is indeed the top right one. So remember, opt of j comma b means you're looking at all the values W1 to Wj with budget b, and what we are interested in opt of W1 to Wn comma W, right? So you want this entry. So what you're interested in is m of W and n, which is opt of n comma W. All right. And as with any recursive algorithm, we have to start off with a base case. So we need to know certain values when we start off. It turns out in this case, you can easily figure out what the value of the first column as well as kind of this bottom row would be. So the question is, what should the initial values be? Okay. And when I say what should these initial values be, in fact, you can know the values even without looking at the actual numbers W1 to Wn and the budget W. John.
Does J represent the indices of the?
The J represents you're picking from W1 to Wj.
Should that be 1 at the lower bound or 0?
0. Right. So when you're saying your budget is 0, that means you cannot pick any other value. I should have mentioned this. I forgot. We are assuming. Yeah. So if the budget is 0, you cannot add anything and get any value.
Is that for the J side at the bottom? There's only n entries.
Right. So it's going to be just these last n entries that are all zeros. Because the budget is 0, that means you cannot get anything beyond 0. And you can trivially attain 0 by not picking anything.
I guess I was just asking, if you go from 0 to n, isn't that n plus 1 base or no?
Oh yeah, it is n plus 1 entries. Yeah.
Oh.
Yeah. All right, so as John pointed out, all of these should be 0. What about these guys? I heard said someone should be 0. Yes, it should be 0. If you're not picking anything, you're not going to get any value either. Okay. So in particular, this entire first row and this entire first column and in the entire either first or bottom row would be 0. Okay. So we know that m of 0 comma j is 0 for all j between 0 and n, so that's n plus 1 values. And m of b comma 0 is also 0 for all budget values between 0 and w, so that's actually w plus 1 values. Right, so right off the bat, even without looking at the numbers, you know what the first column and the bottom row should be. Okay. All right, so now kind of let's try to remember. So we have now figured out the kind of various subproblems that we're interested in. We know what the final value that we're interested in. We also know kind of the base case where to start off. And so now if you remember, the first step of the dynamic programming rules of thumbs was you want to argue that there are polynomially many subproblems. Right? In other words, there are a few not that many subproblems that you need to consider. Okay? So the third question is, how many subproblems do we have? This is not a trick question, Alex.
Times n plus 1?
It's w plus 1 times n plus 1. So the number of subproblems is basically the number of entries in the matrix. I have w plus 1 rows because again it's starting from 0 to w, and I have n plus 1 columns starting from 0 and ending at n. Okay. So the third answer is the number of entries of m, which is n plus 1 times w plus 1. Okay. But asymptotically, it's essentially the same as n times w. Okay. Now, this is polynomial if w is polynomial. If it's not, then this is not polynomial. Okay. So in other words, right. So I'll just make a quick note. This is polynomial if and the reason why I say that is the number of bits needed to represent the number w is log of w and not w. Right? So again, we have seen this before. When you're representing numbers, you think of how many bits you need to represent it, not how many unary digits you need to represent. So as long as w is polynomial in n, this is a polynomial time algorithm. But for say w is 2 to the n, then the number of bits that you need to represent is still n. Right? Because you take log of 2 to the n, but then then the number of entries that you're computing is still exponential in your input size. Does that make sense? Are there any questions on that?
So what
Mark.
happens if w equals n?
If w is equal to n, then it's fine, because then your input size is still n because of w1 to wn. Right, so you have n numbers right there, and then capital W is just log n. So your input size is still theta n.
But wouldn't you have n squared values?
That's fine, it's still polynomial time. So I'm not talking about linear runtime or linear, I'm just saying polynomial, right? So, so there's this number of subproblems is polynomial in the input size as long as W is polynomial in n. If it's not, then it's no longer polynomial size. Okay. And in particular, the algorithm that we're going to see is going to be polynomial runtime if and only if capital W is polynomially small. If it's general, I mean, if it's arbitrary, then it need not be a polynomial runtime. Okay. Any questions on that? All right. So the next, if you look at step 2 of what we wanted from a dynamic programming algorithm, was to come up with a recursive formulation of the optimal, which actually we have already done over here. So let me denote this recurrence by star. So the fourth thing we want to do is we want a recursive formula And this we already have. You just see the formula that we started off. And finally, the third step that we need from the third rule of thumb is we already now have polynomially many subproblems. We have a recursive formula that allows you to compute one subproblem in terms of other subproblems. But now we also need to figure out an ordering in the sense that if you want to compute a particular subproblem in an ordering, it will only depend on things that come before it in the order. Okay? In the weighted interval scheduling problem, the ordering was trivial because you have opt1, opt2, opt3. It was kind of a it was just one-dimensional problems, right? But now in some sense we have a two-dimensional problem because every subproblem corresponds to this matrix. So what we need to figure out is kind of some way of if we want to compute, say, the jth column, how do we do that? In particular, let's say I'm interested in computing the b comma jth entry. And once you're trying to figure out the ordering, what you should always do is go back and stare at your recursive formula. Okay? So let's look at the formula again. So the first thing to note is you look at j comma b, so this entry that we're looking at, it either depends on j minus 1 comma b, right? So if I look at the previous column, it might depend on the column that's in the same row but in the previous column. Okay. Now let's go look back over here. This is actually exactly the same as this value. So if I know j minus 1 times b, I know this and this value. But the kind of more interesting thing is then I need to know this subproblem, which is j minus 1, which is again in the previous column, but the budget is now smaller. Right? So instead of looking at b, if I have this value which says b minus wj, but the important point is every entry, so every arbitrary b comma j entry just depends on two values just in the previous column. In particular, if I had to know the values of the jth column, I only need to know the value in the previous column, and that's it. And so this suggests a natural ordering where you start from the 0th column. That will allow you to compute the first column. And once you're the first column, you can compute the second column, and so on and so forth. So the idea is you go from the 0th column all the way up to the nth column, and once you've computed the nth column, you just look up the top right thing that you're interested in. So in this case, so ordering among subproblems. And I said kind of the main observation here is only need to know the j minus 1th column to compute column j. And actually with that we have answered kind of the 3 rules of thumb. After it's just a matter of kind of writing this down in pseudocode. Before I do that, maybe you guys can talk to your friends for half a minute, let me know if any questions. If not, I'm just going to quickly write down the pseudocode and then kind of run through an example, just filling in some of the entries of the matrix.
Run over every single index.
All right. Are there any questions? Alex.
Does this algorithm always check every single value of m, or is it just like at worst every single one?
So to be pedantic, I have not told you the algorithm yet, but the algorithm we're going to see indeed just goes and fills in every entry of the matrix, every entry, and then at the end just reads the top left, top, I guess, right for you guys and outputs it. And that's typically how dynamic programming algorithms work. You just want one entry, but you're still going to go ahead and compute all of the polynomially many subproblems. And once you've done that, you just output the task. Okay? And the reason why, I mean, one way it kind of smell test for an algorithm with a dynamic programming algorithm is when that is the best you can do. I mean, there's no way to cut shortcuts and get the final value without kind of computing all of the values that. I mean, you can maybe save on some, like for example, in this case, if I really need to know just the top right, I don't need to compute the entire right column. I can just compute the top value, but asymptotically, that doesn't make sense. All right, so now, any other questions? Mac.
You can make the whole matrix, or can you just make it one column at a time?
All right, so let me write down the algorithm and we'll talk about that. Okay. All right, so I'm looking at the problem where I have W1 to Wn, and then I have this, my final bound of W. And so the first step we'll do, and I'll come back to Mark's question in a bit, is you want to allocate, let's say, for now we'll just allocate the W plus 1 times N plus 1 matrix M. Then it turns out, even though I know that this the value of this last row is going to be 0, actually for kind of this recursive formulation, I just will initialize the first column and then just compute all the columns one by one. Okay, and again, I can at the beginning just state all of these to be all zeros, but I'm only going to save, asymptotically insignificant amount of time. So we'll say M B of 0, 0. So the first column is 0 for all B from 0 to W. And then I'm just going to march along the columns, so from J from 1 to N. And for each J, I'm just going to go along, so for each column, I'm just going to fill it from the bottom row to the top row. It really doesn't matter. In fact, you can pick the rows in any order that you want, but it just makes for a simpler pseudocode. So we'll go from B from 0 to W. And then essentially what we're going to do is just rewrite this where we replace the opt by the corresponding M values. Okay. So first we'll check if Wj is strictly bigger than the budget, then MB of J is just the same as the previous J minus 1 value with the same budget. Otherwise, we'll use the max formula in this case. Okay. So in this case, M of B comma J is max of M of B of J minus 1. So this is the case where the jth guy is not in the optimal solution. Otherwise it is, in which case we get Wj. M of the budget goes down from B to B minus Wj. And we're going back to the previous column. Okay. And once we have computed the entire matrix, we are going to return M of W comma N. Okay. So this is basically just kind of writing down in pseudocode what we had seen earlier. The thing to note here is kind of this innermost loop is constant time because you're just kind of reading and comparing only constant many values. And you have two loops that are nested, and so it's like essentially n plus 1 times W plus 1. And this overall is what dominates the runtime. Okay. I mean, every other step that you have is just simple initialization, which is also upper bounded by order of n times W. Okay. Now, 2 comments. So as Mark pointed out, note that to compute the jth column, we only need to remember the j minus 1th column. Right? So we do not really need to remember all the entire matrix to be able to compute the next row. So to compute the jth column, we just need to remember the j minus 1th column, and that would be enough. Okay? And so you can save space. That will not save you time. It would still be order n times W, but that can save you the space of n times W, which could be a big deal. However, this is only true if you're interested in computing the value of the optimal. If you actually want to compute the actual subset of numbers that gives you this thing, you will actually have to remember the entire matrix, because you have to backtrack and figure out where to go. Yeah, Mark.
Can you look ahead and only build the column up to that column plus J plus the next one?
What do you mean that?
You're only going to go B and J minus 1. So if, let's say the column's here, you only have to build the column.
No, but the final thing that you're interested in is W comma N. Right, so again, the final entry that I'm interested in is in this guy. So if you look back at the dependence, this actually depends on all of these values.
Oh, I guess, yeah.
So, I mean, there is, in the worst, unless, I mean, you know something really much more about the input than what we are assuming here, to compute this thing, it can depend on all of the possible values over here. So to figure out, in the worst case, to figure out the actual subset, you have to remember the entire matrix. But if you're only interested in the value of the optimal, then you can just store the previous column, and that would be enough. So let me kind of write this down. So we only need order W space if we only care about the final opt value. But we'll need omega NW space if we want to compute the optimal set S. Okay, because we have to backtrack, and for that we need to know all the values. All right, so what I'm going to do next is do a quick run of this algorithm on a simple input. I'm not going to go through and fill in all the matrix values, but at least kind of walk through a couple of iterations. Okay. All right, so all right. So we're going to do run of the algorithm. So in this case, we'll pick n equal to 3. The weight of the first item is 1. Weight of 2 is 2. The weight of the third item is also 2. And my budget in this case is 3. So in this case, note that the optimal solution is to pick 1 and 2. So let's build the matrix. So it will be a 4 by 4 matrix. Again, reminder that the rows are indexed by the budget B, and the columns are indexed by J. So you have 0, 1, 2, 3 here, 0, 1, 2, 3 here. I said the initialization would initialize the first row to be all zeros. And as we had already observed, this bottom column is all zeros. And even though technically for the run of the algorithm, I should walk through and show that these values should be 0, I'm just going to go ahead and put zeros in there. Okay? And so what I'm going to do is just kind of fill at least this column in. Okay? So let's say we are now interested in M1, 1. So again, just to make sure all of you are on the same page, here the budget is 1. And I'm looking at j equal to 1, and in particular, I'm looking at the number that has value of 1. And in this case, W1 is less than or equal to the budget, so we'll use the max part of the formula. Okay. So this is max of M B comma j minus 1. So B in this case is 1, j minus 1 is 0. Or we pick W1 and we have M of so we have B, which is 1, minus Wj, which is W1, which is 1. And j minus 1 in this case is 0. So all the first column values are 0. So this is max of 0, comma 1 plus 0, which is 1. So that goes in over here. Any questions on that? Okay, so let's now go fill in this value, which is M21, which in this case would be max of M20. The next thing is you put W2 plus M of this budget, in this case is 2, minus W1, which is 1, comma 0. This is max of 0, comma 2 plus 0. Wait. I apologize. Sorry, this is W1. Should probably bring up the formula so that, let's see. Right, so we are looking at over here, again, B is equal to 2. W1 is 1, so I'll have W1 plus M of 2 minus 1, comma 0. Okay. So there's max of 0 and 1 plus 0, which is again 1. M of 3, comma 1, so again here B is 3, W1 is 1, so that's max of M of 3, 0. Times W1 plus M of 3 minus 1, 0. So that's max of 0, comma 1 plus 0 equal to 1. So in some sense, all this is saying is if you're looking at the input where you have only one item, which is W1, and your budget is 1 or more, then the best thing to do is just pick that value. And you'll get a total value of 1. So now let's look at a case where we don't use the max, but this the if part gets executed. So let's look at M. So we're looking at the second column now. Again, the last thing we know is 0, so we're going to look at M1, comma 2. So in this case, B is 1 and W2 is 2, right? So in this case, Wj is strictly bigger than the budget. So this means we're going to just pick up this value over here, which is M1, comma 1, which is 1. Okay. Any questions so far? Okay, so I'm actually not going to go and fill in all the values. I can fill in one value in the remaining matrix if anyone has a choice. Don't care? Sorry? 3, 3. All right. So to compute 3, 3, I actually need to compute this row too. So Christian's choice was this one. So I'll tell you that this, if you work out, turns out to be 2 and 3. And so at the end, we want to compute M33. In this case, my budget is 3. And the weight is 2. So we'll again apply the max formula. So this is max of, we're going to look at this term, which is M of 3, 2. And then we'll have W3. So we'll have, so we have picked in this value. Now we need to pick this value. So we need W3, which is 2. So that's 2 plus M of B minus 1, which is 3 minus 1, and J minus 1, which is 2. Okay. So that's max of M32, which is 3. If I pick, and then I have a 2 over here, so that's 2 plus, this is M22. And so wait, did I? Sorry. This entry is B minus WJ. So this is B minus W3, which is 3 minus 2. So this is 1 comma 2. Okay. And 1 comma 2 here is 1. So this is max of 3 and 3, which is 3. And this is what you expect. So with a maximum budget of 3, the best you can do is pick either 1 or 2 or 1 or 3 to get the total value of 3. Talk to your friends for half a minute. Let me know if any questions. If not, we'll just kind of, we are almost done. We'll just go through some kind of few follow-up remarks on this algorithm. Yeah, Alex.
This final result represents the maximum weight or the total of cycles. Is that right?
Right. So the final value tells you what is the maximum sum that you can get, assuming the sum is less than equal to the budget. It does not immediately tell you what the actual subset is. Okay. So I'm going to talk about that briefly next. But any other questions? All right, so I said this only tells you the value of the optimal subset, not what the actual subset is. But as was the case for the weighted interval scheduling, once you have this entire matrix, it's just kind of fairly easy to compute the actual subset. And basically, all you need to do, and this is true for pretty much all dynamic programming algorithms, once you have computed the actual optimal values for all the subproblems, all you really need to do is figure out kind of a generic scheme to figure out like whether one arbitrary element is in the solution or not. So in this case, we want to figure out if the jth guy is in some optimal solution that includes the first j guys. Okay. So for that, we kind of need to go and look back at kind of a recursive formula. And the first thing to note is if wj is strictly bigger than b, then j cannot be in the optimal solution for the first j guy with budget b. Otherwise, it just depends which of these two is bigger. So if wj is strictly bigger than b, then that implies j is not in the optimal solution for the first j guys along with budget b. Otherwise, we need to check which of the two max values is larger. And so otherwise, if say the part wj plus m of b minus wj comma j minus 1. So again, remember this is the value you would get if you did include j. If this is, let's say, greater than or equal to what you would get if you did not pick j, which is just b and j minus 1, then that implies j is in the optimal solution for 1 to j and budget b, else j is not in this optimal solution. Okay. So this is a simple test to check whether given w1 to wj and a budget b, whether there exists some optimal solution where j is in there or not. Okay. And once you have this test, the idea is you start off from the m comma n entry. First figure out if n is in the optimal solution. If not, you go back and just recursively keep on backtracking. Okay, this is exactly the same trick we did for the weighted interval scheduling problem. So I'm just going to leave it as an exercise so you can recursively compute the optimal subset just like the weighted interval scheduling problem. Okay. So in particular, as an example, if we are looking over here, we look at 3, 3, and we see the two quantities are both the same. So the way we have kind of made this test here, we'll say that 3 is in the optimal solution. So we pick 3, and then we go to this previous part, which is budget 1, and j equal to 1 is equal to this guy. Okay. And so then we go back to m12, in which case we figure out that 2 is not in the optimal solution. So we go to m11, and then we go to m11, we figure out the way we get the value of 1 is by picking the first guy. Okay, and then we are done. So you figured out 3 is there, 2 is not there, and 1 is there. Okay. Any questions on this? All right, before I let you go, I'd like to mention another related problem. I put up a post on Piazza, so I'll keep this short. So it's called the Knapsack Problem. And this actually is a generalization of the subset subproblem that we just saw. So now the ith item has two values. It has this weight and this value wi. And again, as before, I have a budget w on the weights. And you want to output a subset S such that the total weights are within this bound and you maximize the total value that you get so far of Vi. And you get the subset sum problem where the value itself is same as the weight. But the more general problem is there is no necessarily correlation between them. And it turns out that this more general problem is way harder. So there are no known polynomial time algorithms to solve this problem. All right, I'll see you guys on Wednesday.